All right. So welcome to our video number 9 or week number 9. So we are continuing our discussion on robust estimation and filtering. So we have basically been building up our repositories of knowledge and kind of looking at what can happen and with regards to filtering. So essentially, we were looking at fairly simple concepts. After reviewing some of the basics in control systems, we were looking kind of like switch gears and looked at probability and random processes. And from that, we looked at random variables, random process, and then a noise that will be applicable. And then what we're going to be doing is, since we already discussed frequency-based filtering, which is kind of the normal, quote unquote, normal way of filtering stuff, where you try to distinguish. So you think some of the frequencies are extraneous to your system, so you filter out those values. Now we're going to move ahead and then use the fact that our noise could potentially be a Gaussian process and then use that information in our filtering. So we'll start out with doing essentially like a steady state or a static filtering. And then once we are more comfortable with it, we'll actually start looking at Kalman filtering. All right, so what we're going to be doing, or the learning objectives, are going to be the introduction to the concept of estimation, and then we'll solve some least squared estimation problems. So if we're going to do a little bit of a recap, we'll start by estimating scalars, estimating constant vectors, and then we look at least square estimation, and then recursive least square estimation. So without further ado, so here's what we're going to do. So a quick recap, the noise we're going to be looking at is essentially a random process. Again, if you recall, what we mean by random process is a random variable that changes with respect to time. We are going to kind of look at essentially discretized values, but the same concepts would actually apply to continuous values or continuous variables as well. Just it's easier to kind of do the discussion and kind of present the topic with respect to discretized, where the time is discrete. So we're actually looking at individual numbers and then doing the process. The noise in our system is assumed to be a Gaussian white noise. So what do I mean by that? So it kind of would look like shown in the figure here. Conceptually, the processor noise is white if at any time T1, the noise is completely independent of the value of the noise at any other time. So what that means is if I know the value of the noise here, there is no way for me to predict the value of the noise here. It just kind of like randomly jumps, and then it could essentially jump from like a very small value to a very large value and then do kind of anything it wants, and then it's completely random. What we mean by a Gaussian noise is if you look at the noise at any time, the outcome is going to have a Gaussian distribution. So what we mean by that is it's going to have the probability distribution is going to have a Gaussian or a normal distribution. Conceptually, if you think about it, there is going to be more number of points closer to zero. So if you think about this being the zero line, and then there'll be fewer points as you go further and further away from the mean or the zero mean. So the noise is typically characterized by the mean, which is kind of the average of the noise, and then the covariance. Typically for the noise, the mean is going to be zero. If it's not zero, what you can actually do is kind of like recreate a new measurement by subtracting the mean of the noise. So we can, without loss of generality, assume that the average of the mean of the noise is going to be zero. The other value that we're interested in is the covariance, which kind of measures how much the spread of the noise is, and kind of like if it's a very low covariance, that means the noise distribution is fairly narrow. That means a lot more of the points are going to be saturated or concentrated near the zero. And then as the process kind of gets more and more shabby, you can expect more number of points to go and then kind of like be distributed all over the place. So that's what we expect. And we already, as I mentioned, looked at frequency-based filtering. So now we're going to be looking at slightly different concepts. All right. So to estimate the scalar, so let's assume I have 4 different measurements of the length, namely 10.1, 9, 9.5, and 10.5. So essentially, you can either think about having 4 different people make the same measurement, or you used maybe you pick 4 consecutive measurements. It doesn't really matter. The length itself doesn't change within the time. So that's the assumption that we make. So the value is fixed. And so then the question is, what's your best estimation of the scalar? In this case, the length. So what you can think about is the easiest way to do it is to essentially take the average of these 4 values. And then if you did that, particularly if you didn't know the noise or the error, or you assume them to be constant, then we can just assume it's a zero mean. And then if in case it was a non-zero mean, you could potentially subtract it. But your best guess in that case is going to be the average, which comes to 9.775. So this is the easy way to think about it, and this is a fairly straightforward way. So the concept actually extends to a different way. So for instance, if you had a scalar, for instance, say you're measuring the spring force based on the displacement, in that case, X would be the force that you would apply to the spring. So obviously, if you apply a force, you expect the string to get larger, right? So then, assuming the force is fixed, or maybe you have a weight here, and then what you do is you measure how much the spring has actually expanded, and maybe there is some disturbance, maybe somebody is blowing on it a little bit, or there is kind of like the air conditioning that's running, and then you notice that the weight actually maybe oscillates, and then there is a random disturbance, and you kind of take consecutive measurements of these values. You know what the spring constant is, which is going to be the h over here. What you don't know is the weight, and you're trying to estimate these values. And what could also happen is, the other way to think about it is, rather than estimating the constant x, what you can do, which is more likely, is that you're trying to estimate the spring constant. So that's the other way to do it. So what you do is you add maybe like 10 grams, make a measurement, add 20 grams, make a measurement, and then each of that could potentially have a random value associated with it, or random error associated with it, and then you can kind of redo the calculation and then do that as well, or repeat the weights and then still do the calculation. So once again, we could potentially take an average where essentially rather than kind of doing the average of h, so what you can potentially do is average the inputs and average the output, and then based on that, you can try to estimate what the value of h is going to be. So the average of all of my inputs, which is the first elements, is 5 plus 10 plus 15 plus 20 by 4, it comes to 12.5. And then similarly, if I did the average of my outputs, that comes to 25. So if we try to plot this on the chart that we have here, we got h was 2. So we plot that. So this is what we get. So this is the first value, this is the second value, third value, fourth value. And then I plot my line y equal to 2 times x. If I did that, I get a line like this. So the line kind of goes very close to these points, but then if you notice that there's a much larger error with respect to the third point. So the point to remember here is you don't really know which of these values are more accurate than the other. So you can't really say this is a good line, I'm just going to take an average, in which case you're kind of not really using the information that that you want to basically minimize the error relative to all of those points. So let's look mathematically what we're actually doing. So generally what we have is we already know the equation, right? So we have the equation as y equal to h times x. So what we're doing is we can think about estimating the value of h. And since I don't know the value of h, I'm going to kind of make a guess, and I'm going to use h hat as my best estimate for my value of h. So in that case, what will happen is for each value of x, I can multiply that. I can basically multiply h hat times x to get a new estimate. So this is going to be different from the actual value of y that you get based on the value h you might choose. So in that case, what is going to happen is if I measure the difference between the actual measurement I get and then the value I get here, So for instance, if I took the value of h to be h hat to be 4, then the difference between the value I get y minus h times x would be fairly large. So as I get h hat to be much closer to the actual value of h, my error would start to decrease. But we have to remember that because there is some uncertainty in the values of the estimate due to some noise or measurement uncertainty, the y hat would never be exactly equal to the actual value of y. So what that means is if I subtract y minus y hat, I'm going to get some error. So we'll call that E, which is defined as y minus y hat, which is equal to y minus h hat x. Right? I'm just going to substitute the value for y hat from here. So what happens is I can calculate the value of h. So what we basically did is we kind of took the average, which is the same as setting the average or the sum of all of the errors, because we're setting it to 0. We kind of like ignore the n, but essentially what we did was we basically said I'm going to set the average error to be 0. What we're going to be doing instead is using a cost, which is going to be squares of the error, sum of the squares of the error, which is actually going to be equal to E1 squared plus E2 squared plus so on and so forth, which can be written as sigma E squared. The reason we are doing that is that the averaging doesn't work too well, particularly in the context when X could potentially be vectors of more than one element. So in that case, you can't really do an average and then calculate the value of H. So that's the reason we are doing this. And mathematically, the square cost function is a lot easier because as we'll see, we can do kind of like a derivative with respect to H hat, and then it kind of gives you a nice result. So again, so there is nothing really sacrosanct about the square or choosing the cost function to be the sum of the squares of the error, just that it makes mathematical sense, or it makes the mathematical calculation a lot easier. There is nothing stopping you from taking the fourth power, which would just make the mathematics very difficult to actually do the calculation. So we're going to stick to the square of the error. The main advantage is this basically becomes nicely written as an inner product between the error. So essentially E is going to be, say, a column vector, and then if I multiply that by a row vector, I'm going to get just one number. So we have to keep in mind that the J, the cost function, is going to be just a scalar or a single number, which is given by sum of the squares of all of the errors or the inner product. So all of those are going to give you the same result. So once you have this, what I'm going to do is I'm going to try to find an H bar that minimizes the inner product or the sum of the squares of the error. So how do I do that? So if you recall from a calculus, if you want to minimize with respect to some variable, then what you do is you take the derivative of the cost function with respect to that particular variable. So for instance, if I had like a curve where it's an f of x, say f of x equal to x squared, then if I take the second derivative, I can find the minimum. We do a similar thing here, just that instead of it being taken derivative with respect to x, since x and y's are going to be constant, we're going to be taking the derivative with respect to the variable or the tuning parameter. So in this case, it's going to be h hat. So if I did that, I'm going to take the derivative and then set this is equal to 0. And then ideally, you would want to check by taking the second derivative and then checking the sign of the second derivative as well to ensure that the cost is actually minimum. So once we do that, let's do mathematically see what's going to happen. So we're going to use the chain differentiation rule. So dj by dh is going to be d by dh hat of E transpose E. So we're going to substitute for E transpose and E as our inner product. So this basically becomes y minus h hat x. So keep in mind y is going to be a column vector. X is also going to be a column vector. So if you take a transpose, so this is going to be a column vector as well. And so once you take the derivative, essentially, or rather this product is going to be just a scalar. And then what you're doing is you're taking the derivative. So this actually becomes 2 times y minus h bar x transpose times d by dh bar of this term. So this actually comes from the calculus So essentially what we're doing is we're taking the derivative with respect to each of these terms, and then because of the symmetry, this actually becomes 2 times y minus h hat x transpose times this derivative. So if I expand, since y is constant, the only variable here is going to be h hat. So the derivative, this term, the derivative of y with respect to h hat is 0. The derivative of this term with respect to h hat is just going to give me x, or minus x in this case, because there's a minus over here. And so we're going to set, if we set this term to be 0, we multiply this. So this becomes minus yx minus h hat x transpose x. And so this becomes y transpose x minus h hat x transpose x equal to 0. And then now the only unknown here is going to be h hat. So we take that to the other side, and then we get h hat is y transpose x divided by x transpose x. So this works. So you can actually divide it like this if it's a scalar. If it's not, then you need to use a matrix inverse. So essentially, h hat will be y transpose x times inverse of x transpose x. Let's do that in this case. So if I substitute in the values, I get 11 times 5 plus 21 times 10 plus 27 times 15 plus 41 times 20 divided by the squares of the x's. So if I did that, I get about 1.9867. And so you notice that if I actually substitute and then draw the line, it's not too different from the original line, mainly because we have more number of points over here which have a lower error, so it kind of balances out. But this is kind of mathematically how you would do the calculation. So next, we're going to be looking at estimating a constant vector. So essentially, we have x is a vector, x1, x2, x3, so on up to xn. So it has n elements. And then you have a measurement here, noisy measurement. Y1 is h11x1, h12x2, so on and so forth, up to h1nxn plus v1. So what this means is there is a measurement, like a single measurement, which is some known combination or known summation of the input vector. It also has a noise v1 here. And then similarly, we have a y2, which is a second measurement, which is potentially slightly different combination of the x's plus another noise term, so on and so forth. So what we have are essentially k measurements over here. So we'll see just shortly that if the number of measurements that you have is less than the number of vector elements, or basically if k is less than n, you can't really solve this problem. So it's like saying, okay, I give you a single measurement. So for instance, in the bottom, if I just tell you 2x1 plus x2 is equal to 3.1, and then if I ask you to solve for x1 and x2, you can't really solve this, right? So I give you only one measurement, and then there are two things you need to estimate. The best you can do is kind of try to estimate x2 in terms of x1, but that's the best you can do. So for this to work, the number of measurements you have, yk, or the number of measurements k, should be at least equal to or greater than the size of the vector. So that's one of the necessary conditions. What you would also need is you need to have another restriction that these should not be linearly dependent on each other. What that means is if I just tell you 2x1 plus x2 is 3.1, and then if I give you 4x1 plus 2x2 equal to some other value, you can't really solve the problem either, mainly because you're kind of giving you the same information just like doubled, and that isn't really an additional information that you can use to solve the problem. So those are the two restrictions. So we're going to assume the number of measurements is greater than the number of elements here, and also that the combination of h's is such that the equations aren't linearly dependent on each other. So there's a mathematical way we can write that. So we'll see that shortly. But nonetheless, so what we are trying to do is we are trying to estimate x given all of the hij. So this is kind of a slightly different way. You can kind of like rename h's and x's As long as you have one set that's known, you're trying to estimate the other set, that's fine. So what we do mathematically is we can write all of these equations as a summation. So I basically write the first equation here, where I runs from 1 to k. So I say y1 is h, and then ij. So what that means is if I is 1, then it'll be 1, and then j runs from 1 to n. So it becomes hij times xj plus so v I. So essentially what I'm doing is each of this term actually represents the term over here, and this summation here represents each one of these lines over here. So again, so coming back, so the example would be, so given two measurements over here, 2x1 plus x2, and then y1 is 3.1. So the way you can write that as is 2x1 plus x2 equal to 3.1, and 3x1 plus 3x2 equal to 5.2. So if I do that, what I can do is, since I have only two equations and two unknowns, I can solve this equation, right? So if I subtract the first equation from the second equation over here, so I would get, or rather, I need to subtract essentially 3 times the first equation minus the second equation, and then I can figure out what this would be. So if I did 3 times this, I'll get 6x1 plus 3x2 would be equal to 3 times this number, and then I subtract, I'll get 6 minus 3, I'll get 3x1. This terms would cancel out, and then you get just one particular value, and then you can solve that value for x1, and then you substitute that equation back into either one of these, and then you would get the value for x2. So this, given two equations and two unknowns, you can kind of solve it, but this is not what we're going to do. So let's imagine I'll give you a third input as well. So just quick note, so if you have two equations and two unknowns, you can solve this. So if I give you a third equation over here, now things get a little bit dicey. So these are three equations, and if I kind of consider the first two equations, I might get one solution for x1 and x2. If I consider equation 2 and 3, I might get a different solution. If I consider 1 and 3, I'll get a third another solution. So then what do I do? So one way you can potentially think about doing is you can try to calculate all possible combinations and then solve for x1 and x2 and then try to take an average. So that's one way to do it, but that's going to be fairly tedious, particularly if I give you, say, another equation over here, then, or maybe another fifth equation, then as you take 2 by 2, the number of choices gets much larger, and this is not the way we would do it. So what we'd rather do is we would try to figure out a least square method of finding the best solution, knowing that we have some errors in the measurements wise, and then how best to calculate the value of x given the set of equations. So that's the objective of the least square estimator. The other way to do it is we are trying to minimize the least squared error in our estimation of the unknown vector constant. So rather than looking to do averaging, we are basically trying to do something that's slightly better. So what we do is, imagine we have this set of equations here. So what I'm going to do is, if my xi's hats are my estimate, so what I would do is kind of like add a hat to all of this. So my y1 hat is all of this. So basically, since my h's are constant, I keep it as is. When I put in my estimated value of x1 to n, I get an estimated output. Similarly, I'll get an estimated output y2 hat, so on and so forth, all the way up to yk hat. So right now, I basically had, essentially I have an estimate of x, and then if I substitute that, I'll get an estimated of value of y. So because of the error, like we mentioned before, the e's, what will happen is if I subtract these two, even if my estimation is exactly equal to the actual state, I might still expect some errors in my y hat. So what I do is, if I let's define the error as epsilon I is y minus y hat of I. So then what happens is, if my so essentially I can substitute this value back, right? So essentially my y's I know, this is defined over here. So epsilon just becomes minus h x hat, because the h here is the same as, or it's known, so I can kind of use the value of h. And then what we try to do is we're going to minimize the value of this error over here. So keep in mind this epsilon actually has two components to it. What the first component is going to be the fact that my x hat isn't going to be exactly equal to my x's. So that's going to contribute one error. And on top of that, there is a little bit of a measurement noise, and that's going to contribute to a second error. So essentially, the epsilon i's, which will be the elements of our vector, is going to have two components of the error. What I can do is so since we are assuming that x, so we basically want to make sure that the x hat approaches x. So the best we can do is kind of minimize the error here and then hope that all of the error is just because of the noise. And then if we can minimize the epsilons by choosing x hats appropriately, then if it's all set up properly, then if we minimize it, we are basically just going to capture just the effect of the noise alone, and that should allow you to estimate the value of x's using the least square estimator. So that is the basic principle. So what do we do? First, we define the cost function. The cost function is going to be the sum of the squares of all of the errors. So that's going to be j is epsilon 1 squared plus epsilon 2 squared all the way up to epsilon k squared. And then this can be written as the inner product epsilon transpose epsilon. So essentially epsilon is a column vector, and then epsilon transpose is a row vector. So if we multiply both of these, you're going to just have one single scalar number over here. So we're going to substitute for the values of epsilon from the previous equation here, and then if we do that, we find this would be equal to y minus h x hat transpose, and then y minus h x hat. The values of here, so the values of h is known, the values of y is known, right? So what we do is then the only thing we can vary in this equation is the x hat that we can kind of like fiddle around to minimize the error. So what we do is we differentiate the cost function j with respect to our variable or the tuning parameter. And so what we do that, so again, because of symmetry, and then you can basically use the chain rule, and then you're going to get 2 times this term plus differentiation of this term with respect to x hat. So that gives us 2 times y minus x h x hat transpose times minus h. Again, so I refer you back to our discussion on matrix calculus to kind of figure out how where this comes from. And so if we do that, now we can set this equation to 0, and that will allow us to minimize the values. So here, if we do that, so we expand this. So we expand this out. We can potentially take the transpose. We get h transpose y minus h x hat equal to 0. And this gives h transpose y is h transpose h x hat. The only thing is we take the inverse of here, h transpose h. And so this we get x hat would be h transpose h inverse h transpose times y. So if you look at the dimensions here, so we would basically have a lot more of these y's over here. And because you're doing the h transpose h inverse, h transpose h would be a square matrix. And this is where we need h transpose h to have full rank, or it needs to be invertible for the whole system to work. What we then do is we define this term here, h transpose h inverse h transpose, as the pseudo left or left pseudo inverse of h, and this inverse exists if k greater than n and h is full rank. So again, recall when I mean full rank, that means the whole this has so this has n rows. That means there are n linearly independent rows or n linearly independent columns. So that's the only time in which the inverse would exist. So let's do example 3.1 in the book. So we are given k noisy measurements of a scalar, and then we're trying to figure out what will be the best estimate of the system. So what does that mean? So essentially we have y i's of the form x plus vi, where vi is some arbitrary random noise or assumed to be Gaussian uh, process. And then what happens is we have hi1 is equal to 1. So essentially we just have like one element. So that means if I write my H matrix, that's going to be just 1, 1 all the way to how many ever measurements you have. So if I calculate the transpose, H transpose, that is just the same ones, but then arranged in a row format. So that it becomes 1, 1, 1 in a row format. So then if we recall, what we need to do is calculate H transpose H. So that just becomes 1, 1, 1, 1. And then this has k elements, this has k elements. So this would have k elements here. So if you add 1k times, you just get k. Hence, if you calculate the pseudo left inverse, it just becomes 1 over k. And then because H is 1, and then if you multiply that with y, you just end up with 1 over k, and then all of some of the y's over here. So what that means is we are actually just calculating the average of the system. So essentially, if you're having k measurements of a constant, the best estimate that you have is the average of the measurement. So let's do the example that we started out. So we have 2x1 plus x2. We get y1 equal to 3.1. With 3x1 plus 3x2, we get y2 is 5.5. 4x1 plus 3x2, we get y3 is 7.1. So I do have a hint here as to how you would calculate a 2 by 2 matrix. So you'll see you'll actually end up with a 2 by 2 matrix. So we wanted to calculate the inverse. So we calculate the adjoint. So the adjoint is just made by swapping the diagonal elements and then reversing the signs of the off diagonal elements. So we get D minus B minus CA. So that's the adjoint. And the determinant is product of these two minus product of these two. And so that becomes AD minus BC. And the inverse is determinant inverse times the adjoint of M. So this will be useful for this problem, which is what I'm going to use. But obviously, if you have a scientific calculator, you can just directly type in the inverse and it's going to give you the value. Just this might be another way to double check that you didn't make some mistake in entering the values, or something really something that could be easily avoided. So coming back, so we are going to write this in our standard form. So the first equation is going to be k equal to 1. And then this is going to be I equal to 1, I equal to 2. So then we can write this in this form. Ya is sum hij xj. So that means I get from the first equation, I get h11 would be this term 2. H12 would be this term. H21 is 3. H22 is 3. H31 is this term 4. H32 is this term over here. And then y1 through 3 is already given to us. So we have that. So we can write H in the matrix form. So it just becomes 2, 1, 3, 3, 4, 3. We calculate H transpose, which is just replacing or swapping the rows and the columns. So we get 2, 3, 4 first row, 1, 3, 3 in the second row. So next we need to calculate H transpose H. So it just becomes 3 times 2, 2 times 2 plus 3 times 3 plus 4 times 4. That will be the first element, and then we kind of just do the multiplication as you would. Again, if you have the scientific calculator, you can just put in H transpose, or most of them should be able to calculate the transpose as well. And then based on that, you should be able to calculate the the product H transpose H. Nonetheless, if you wanted to do it manually, you could. So that just becomes 29, 23, 23, and 19. So make sure that you double check. This would always be symmetric, essentially because you're multiplying it in this format. The diagonal elements, the off diagonal elements need to be the same. So next we'll take the inverse here. So because this is a 2 by 2 matrix, we can use a trick that we just had, or use the hint that was given to you. So for 2 by 2 matrix, we have this in the form A, B, C, D. So A would be 29, B and C is 23, and then your D is going to be 19. So you can substitute into the formula over there. So the determinant is 19 times, so 29 times 19 minus 23 times 23, which comes to 22. The adjoint is going to be swapping the diagonal elements and reversing or flipping the signs of the off diagonal elements. So we get 19 and 29 here, and then the off diagonal elements are going to be minus 23. So then I'm going to divide this by 22, or I'm going to multiply it by 22 inverse, both are same. So that gives me 0.8636 to about 4 decimal places, and then minus 1.0455, minus 1.0455, and then 1.3182. So we have all of the steps lined up, excuse me. So I have H transpose H inverse. So then I'm going to multiply this by the H transpose to get the left pseudo inverse. So I get H transpose H the whole inverse times H transpose. So that is just this number here times H transpose that we calculated. So we multiply, you get this times this plus this times this. So again, if you have the scientific calculator, you can, which I highly recommend, that you can get this value, and this comes to 0.6818, and this is minus 0.5455, 3182, 0.3182, 0.7727, 0.8187, minus 0.2273. So this is the pseudo left inverse. And then now I'm going to multiply this by y vector, which is going to be y1, y2, y3 to get h hat. So I multiply this, which gives me h hat is 1.3727 and then 0.4509. So notice that we had two unknowns in our x's, and then we have more equations, but nonetheless you get able to kind of like do some aggregate, and then you end up with two elements. So that's what you expect the problem to do, or the method to do. So next we're going to look at what's known as the weighted least square. So this is kind of an extension of the least square method we just discussed before and solved the problem. So the previous assumption, or the previous case, what happened was you assumed all of the noises had the same size, or the noise covariance. Then you could just like minimize kind of the overall sum of the noise. So essentially what you're doing is you're minimizing the sum of E1 squared plus E2 squared plus so on and so forth. Another way to think about it is you're basically calculating kind of the overall estimated value, and then you're minimizing it. The problem with that approach is that if your individual noises have slightly different covariances, then you might want to give slightly different weightages to the errors. Just simply because if you have a higher covariance in, say, the first noise compared to the second noise, then you would want to potentially give a lower weightage for the first noise, because the second one is more likely to be accurate. So that's what we're going to be doing here. So where previously we had V1, V transpose, we didn't really care about it. We assumed all of that had the same noise covariance. So here we're going to assume the noise covariance are sigma 1 squared, sigma 2 squared, so on and so forth, up to sigma k squared. All of the other elements are going to be 0. So if you calculate the expected value of V transpose, we're assuming the noises V1 and V2 are uncorrelated, and then the covariances are sigma 1 through sigma k. So again, we use the same formulation. Everything else kind of remains the same. So where in the kind of like a compressed form, you write it as yi is equal to sigma j running from 1 to n hij xj, excuse me, plus vi, and then we do the estimated value of y hat, where if x hat is the estimated value, we just substitute for x hat. Since the mean of the noise is 0, we put 0 over here, so this will be the estimated error. Again, if you recall, even if x hat was exactly equal to x of j, then in which case the errors only be because of the noise. What will happen is that the sum each of these expected value, this is going to be sigma squared. So what you typically want to do is you want to minimize this, right? So if sigma 1 is much larger than say sigma 2, then you might want to kind of scale it down appropriately. So what we can do is essentially think about dividing all of the square errors by the sigma I squared, which seems to be the natural weighing function that you can use. So if I did that, so what's going to happen is we're going to define the new cost function as j equal to epsilon 1 squared by sigma 1 squared plus epsilon 2 squared by sigma 2 squared, so on and so forth, all the way up to epsilon k squared by sigma k squared. So then if you notice in vector form, so this just becomes E transpose R inverse, epsilon transpose R inverse epsilon, right? So essentially, if my R was identity matrix, or all of the noise had the same covariance, or covariance equal to 1, then we get back the least square estimate. So if you, again, coming back, so we're going to follow pretty much the same steps that we had before. So then if you substitute for epsilon from the previous page, where epsilon is equal to y minus h x hat, and so this becomes y minus h x hat transpose R inverse times y minus h hat. The principle still remains the same. The only thing that you can tune is my x hat. So what I'm going to do is I'm going to minimize with respect to x hat by taking the derivative of dj with respect to dx hat and setting that equal to 0. If I do that, I get 2 y minus h x hat transpose R inverse times minus h equal to 0. So we multiply that out, factor for x hat, and then we get x hat would be equal to h R inverse h, the whole inverse, times h transpose R inverse times y. So again, if I put R equal to I get back the previously squared. So what we again need is, so we need this term h transpose R inverse h to be full rank for this thing to work. So let's redo the previous problem where we have 2x1 plus x2 has a covariance of 0.01, y2 has a covariance of 0.25, y3 has a noise covariance of v3 has a covariance of 0.01, and then we're going to assume that the noises are uncorrelated as well. So now would be a good time for you to pause the video and then solve this and then verify the results. So again, my h is remaining the same pretty much. So I get h is 213343. The other value is my r is equal to the expected value of v transpose. So then I get my diagonal elements of 0.01, 0.25, and 0.01. And then because my expected value of vij is 0 if I not equal to j, then all of the off diagonal terms would be 0. So then I write my r in this format over here. So then, if you recall, the formula for calculating x hat would just be this over here times y. Again, if you have the scientific calculator, you can kind of do and then calculate the value, but I'm going to run through all of the steps just to make sure everybody's on the same page. So for this, we need to calculate R inverse, which is this inverse. For a diagonal matrix, the inverse is just the inverse of all of the diagonal elements over here. So this just becomes 100, 400. And then H transpose R inverse is going to be 2, 3, 4, 1, 3, 3 times the 100, 0, 0, 0, 4, 0, 0, 0, 100. So if we multiply that out, I get 200, 12, 400, 100, 12, 300. So then we multiply this by H. So this is what we get. So we multiply this out and then we get 2036, 1436, 1436, 1036. Again, so you can use your scientific calculator to calculate the inverse, or we can use the adjoint and then kind of calculate the determinant and use that method. So if you did that, so the adjoint of this matrix is going to be flipping the diagonal elements. So this becomes 1036, this becomes 2036, and then switching the signs of the off diagonal elements. And then I calculate the determinant, which is going to be 2036 times 1036 minus 1436 squared, which comes to 47200. So to calculate the inverse, I divide the adjoint by this number, which gives me 0.0219 minus 0.0304 minus 0.0304 and then 0.0431. So then we multiply this by H transpose R inverse, so that we already calculated. So we get multiply this out, and then we get 1.3475 minus 0.1017 minus 0.3475, and then minus 1.7712, and then 0.1525, 0.7712. And then we got to multiply this by y's, multiply this out, and then we get x to be 1.1508 and 0.8237. So this is how it's all. So this concludes our discussion on kind of least square, and then how you would actually use in case there are two ways. So in case your all of the covariances were fixed, then you'd use a normal least square, and then in case you have the covariances being different, you could actually use a weighted least square where you take the inverse of the expected value of the noise covariance, or the expected value of V transpose V, or the values of the noise covariance. So next we're going to introduce the concept of recursive least square. So imagine when you're measuring there's an unknown value, rather than getting all of the values, you have values that you get of this form. So you have HK is 2, and then I get Y1 is 0.69 with a noise 0, 1. What this means is it's 0 mean with a sigma squared, or the noise covariance of 1, and then we get Y2 is 1.39, V2 is 0, 2, normal distribution with mean 0 and covariance 2, and then Y3 is 2.59 with a noise covariance of 3, and then Y4 is 9.16 with a noise covariance of 4, and so on and so forth. So we get all of these values. So what we previously did was we kind of could potentially arrange all of these, and then essentially use our weighted least square to calculate the values. But this gets a little bit tedious, particularly when your matrix size starts to grow. And if you the other thing is, if you have 10 data points that you already calculate all of your values, now if I give you 11th data point, what you need to do is kind of go through all of your calculations again, right? So you need to calculate the H transposes, and then the H transpose R inverse H, and then take the inverse, do all of that, go through the whole process. So which could potentially get a little bit more tedious, and this is not very efficient, and this is particularly relevant. So this is where you would use a recursive least square, and this becomes particularly relevant if your data is going to arrive sequentially. So this is what we're going to be doing in the next video, where we would kind of look at an extension of the least squared estimator using the recursive least square. And then once we are fairly comfortable with the recursive least square, that becomes a jumping board for Kalman filtering, because you can think about the Kalman filtering where your data is going to come in sequentially, but your X is also going to change. So that just is going to make things more interesting. So this basically concludes our video for week 9. So what we did in this video is we did some kind of like, after reviewing the concept, we were looking at ways we can actually estimate a constant. So we looked at estimating a single value. Then we expanded our scope and said we're going to estimate a vector. And then we said what happens if you're estimating a vector with noise, which has known covariance, which is potentially different. And then we finally started looking at why you would, or where you would potentially be using a recursive least square. So this ends our video, and thank you for watching, and then see you in the next video.